So as I'm in Singapore, I just wanted to mention briefly, we kind of have a worldwide presence, so we have a number of process and application developments through the world. And particularly there are 4 competence centres, one based in Eindhoven, which is where our headquarters are. We have one in the US, one in Filton in the UK, close to the aerospace cluster there. But the one I wanted to talk about was one that's going to open very soon, and that's one in Singapore here to kind of do that. Just to say a little bit more about that, each of the competence centres has their own specialism, and the one in Singapore, it's really focusing on AM industrialisation, and it's really focused on the semiconductor and the aerospace manufacturing that's kind of focused here. And particularly then its integration with post-processing subtractive technologies as well to do that. And I would like to see that there's one of my colleague out there somewhere, Mike Go. He's the general manager of the centre. So if there's any questions, then please come to me or contact Mike with the email address to do that. Okay, so to start a little bit more on the main point of the presentation, why are there relatively few alloys used in metal AM? I want to kind of answer these questions. So could it be to the composition of the material itself? Does that cause problems, some of the alloying elements? Are they suitable for the process? Is it the processing conditions we choose? There's a wide range of parameter sets we can choose on the machine. Are we actually choosing the best ones to get the material processing the way we want to? Or is it even external influences from the AM case study itself that affect the materials and the development as they come along? So let's start looking a little bit into that. Here I'm just going to talk about one particular material in itself. So what we see often in AM is that all the advantages you can get from the design of AM, it's used in applications that are really kind of demanding, and people want that, and they also want the part to have great functionality, but they also want the materials to be high performance as well. And the ones we just want to look at, or the ones I'm going to speak about now, are superalloys. This is a really important group, particularly for high temperature applications, and aerospace and space in particular are interested in these materials, particularly because they want to use them in the hottest sections of jet and rocket engines, really gas turbines. They can kind of be based in a number of base materials, so nickel, iron, nickel and cobalt, but really have a set of unique properties. So they all have good strength, ductility and creep at high temperature, and also the corrosion resistance is really good in these applications. So just the graph on the left there really is illustrating some of the materials we got plot on the graph. So the 2 axes of 2 of the alloying elements in there. And what we have is this kind of imaginary line that as we move from the bottom left to the top right, we have materials that become increasingly difficult to weld in this case. Now, obviously our process, AM, isn't welding, but there's a direct correlation between the two and how well they're going to be processed in the system itself. So as we can see in the bottom left, we have the materials we're kind of used to in AM that are commonly available, so things like 718 and 625. But also as we move up then, we have some of these more desirable materials that aerospace are interested in, particularly. And one material I want to pick out is CM247LC, which I don't know how familiar that is to people, but it's really of interest to the aerospace sector. They're very interested in this material, and there's been a lot of research in the literature about trying to use this in the process. However, it doesn't work particularly well in AM to do that, and isn't really a material that's been designed to do it. So these difficult to weld materials really are susceptible to cracking. The grain boundary has a liquid effect, and this is where the cracks form between these grains, and that's driven by these residual stresses and thermal stresses we see in the process. And the image we just have at the bottom there is an example of a part built in AM, or laser powder bed, and you can see all the cracks that produce. So these aren't pores or anything else, it's fully dense, but we have a cracking effect that helps, and obviously isn't good from a part point of view to do that. So what I'll talk about in the rest of the presentation is then why the interest is there to do it. So why are people still trying to use materials that are not very suitable for the process? And I'll go into explain that in a moment. But really how we see material development in additive industries really it's a gateway to new applications. So the material itself, for example, if you do copper, this may open new applications. So copper might be of interest for rocket engines because of the coolings you can do with that. But then we see actually the applications then drive really the new cost and expand the uses of that. And a good example is medical, perhaps, where acetabulum cups have been common, but by driving down the cost, we're seeing then new applications that really open up and then make economic sense to kind of do that. And because of our technology, where we automate a lot of the systems, we're continuing to drive down the cost of the part. And actually, for certain parts, we're seeing 40-50% of the part is actually the cost of the powder. So many of our customers are now really seeing that pressure on the powder supply and driving down the cost there is a significant part of reducing the overall cost of the part to do that. So let's just say a little bit about the business case. So this in itself could be a presentation. There's obviously drivers as cost and design for that. But there's three in particular essential factors I think we really need to help with industrial AM components. That's material, process, and data. So the material side, it's clear we've got to start with good material. This is really only the input. It's as good as, well, the output is only as good as the input you put in. We need to learn how to specify these materials, control the quality, the environment they're stored in, the recycling, and things like that. We have the process side as well, which is really the machine part. We need all the good things there, the process parameters, the stability, design for AM. But the point I particularly want to talk about is the importance of data to do that. And this is really where we're going from the industrial side of things. It's important to have that data set, the process variations, statistical analysis, what it is. There's a long list, material data, design allowables, to kind of do that. But that's really the key that enables a certain interest is to get into it. So my question before about why is CM247 important, why are they still wanting to use material, it's because aerospace have a lot of data on that material, and the tests to do it, fatigue at high temperatures is expensive. They've got the experience. They really want to use that material if it's possible. And that's simply because if you look at using a new process, which is AM, with new materials on a new design, that's much too scary in the sense of too high a risk for aerospace companies and people to use. So they want to kind of lower their risk. And one way of doing that is trying to stick with a material they know, a part they know. So often aerospace don't jump to all these amazing parts you can make with AM. They stick with the replacement part to do that. So they only then kind of qualify the process to do that. Now what's exciting is a lot of these companies, and it's not just limited to aerospace, but have really started to qualify the process now. And now they're really starting to say, okay, we've done it in a 718 material, now we really want to do it in the material we're really interested in. And I think now we're going to start to see more and more materials come through. Obviously those companies that are kind of less risk averse can take new materials on and new processes and new designs much quicker to do that. And I'll talk about some of our customers who do that later on in the slides as we go on. Okay, so what can we do in the future to expand the range of materials? So I want to just talk a little bit about intelligent processing. I won't read that out. You can have a read through yourself as I'm talking. But the three bits highlighted in bold were just the ones I wanted to talk about, particularly model-based process optimization, the in-situ microstructure, sensing, and then control of the process. Now, these are the ideas have been around for a long time. So this is 1998, and there's even before that. But only really now is the technology coming around that actually we can do these things. So the in-situ sensing, we have now processes we can actually measure that much more efficiently, and computers and simulation and things have really allowed the model-based process to develop as well. So one of the projects we have insight in then is a project called MAP. This is with Ian Todd at the Sheffield University in the UK. Is doing a lot of work here. And what they're doing really is to look at the process modeling, the control, and the optimizations, the MCO, complex processes. And this is where they're using all this data-centric informatics, machine learning, artificial intelligence to really put some insights into the process and the materials we want to do now. What they're looking to do is they see the current situation with materials as being variables, that the input is not controlled properly, the process is fixed, with limited monitoring to do that, and the parts you then get out are variable to do that. What they want to see, and some of the work I'll just present in a moment, is actually they want the material designed for the process, so that could be new material specific for AM, but actually have a high chance of working with the part they want to do. And then as we develop processes, they're much tighter monitored, have dynamic control and machine learning and things, you can end up with parts that are truly designed with quality built in to do that. So modeling-based processes have come a long way now recently. So if you look at the image on the left, again, this is some work from University of Birmingham. They're really starting to model kind of the solid to liquid transitions and then back to a solid. So they start off with the powder, we're melting that, and how it returns then to the parts we see. But anybody who's seen the high-speed camera images of the effect of this process can see all the particles that get emanated. It's really quite a viatolic process in the chamber as we see and melt that, and that's making some great stuns, great progress in modeling that situation. The image on the right is one of our partners, so Ansys 3D Sim. They're really good at now modeling the process itself, and particularly coming up with things like deformation of parts to do that. So this modeling part of this, relating that back to this intelligent manufacturing, we're starting to get near with the modeling-based process side of things to do that. And similarly with the sensing side of things, we're making great progress there too. The image on the left is some academic work that's really quite interesting. They've managed to put a mock-up of the kind of laser powder bed process in a synchrotron kind of source, a diamond light source, and they're then using high-speed imaging to actually get really good insights into the process itself. Please look at the links, there's some really interesting videos there to see that. But of course, not everyone's going to have access to a big synchrotron, so there's also in-process monitoring as well, so we're working with Signalite to do the melt pool monitoring as well, and there's all kind of information you can get from that process too, to give you more insights into what's actually in the build, happening in the build chamber as we build to do that. So you put that all together and then back to the map project, so some of the work Todd's done there. So again, back to this material, CM247, that I was talking about earlier. The images on the right is with some DOV and a lot of hard work and testing. You can get some reasonable results, so a good density. But the point is, it kind of takes 6 weeks of development time, lots of testing to do that. What they've demonstrated with the map project and the AI they introduced is that through machine learning they can get that down to kind of 6 minutes to do that. And what's exciting for me there in terms of new materials then, it's not always about having to trial new alloys and everything that's happened historically and taken decades to do. We can actually process or simulate the process and actually come up with what alloys are going to work well to start with in the process. Okay, so there's just a few slides, or just a slide here I wanted to talk about. There's obviously lots of other things happening in the industry, not just what we're doing at Additive Industries. And just 2 points here. The part on the left I think is really interesting because what they're doing there is using the process itself to change the material in itself. So what they're doing is different process parameters to generate a coarse microstructure which is beneficial for creep in the blades. This is the image I showed earlier. But then they're changing it for a fine microstructure which is beneficial for fatigue then in the root of the blade itself to do that. So rather than have these generic material parameters that everyone uses, we ended up with kind of feature specific to give you the properties you want in the areas you want. And I think that's really an area of the interest in for the industry to go in from that. And also from a material side, this was a paper printed in Nature, and now is a company, HRL, and they've done some really basic metallurgy to actually make the materials that were hard, these unweldable materials, to actually put things of benefit to the process to do that by adding nanoparticles and things. Again, a really interesting approach to help develop further the materials for our industry. Okay, so I just wanted to kind of then move on to, we have some materials already, what can we do with those? And I think we can do a lot more than many people see to do that. I think this is now a video for one of our customers, so K3D, as I say, talked about their smaller company, essentially in bakery lines, and they've come up with some really nice innovations. So instead of listening to me talk for a while, you can listen to Jaap and watch the video.
In this movie, you see an industrial bakery production line. Different robots with cutting tools attached to the end will make cuts in dough pieces. This part is attached to the end of the robot. It consists of 20 products, it's pretty heavy, and dough will stick to the knife.
The solution was found in 3D metal printing. This leads to a total new way of designing and producing parts.
The blade of the knife is printed porous. By putting on air here, a thin layer of air will be positioned around the blade. With this knife you can perfectly cut into dough pieces without having sticking effect of the dough onto the knife. Here you see the comparison between the old and new design. The weight has been reduced from 811 grams to only 80. Also the production price went down with 60%, and the same holds for the lead time. The number of parts was reduced from 20 to 1. Here you see the porous knife. Air will be delivered here. It goes through the leaf spring, through the bearing, to the porous structure. We went from 20 parts to only 1. We included the knife, a bearing point and a leaf spring.
So I think for me, this is a really nice application. So it shows all the good things that you can do with AM, all the weight saving and everything else that you achieve with good design from that point of view. And they recently won a TCT award for their design as well to do that. But the point I wanted to make today, as well as being a great design, it's also about materials. So here we have a number of different elements where they've really thought about the material and the uses they're going to do that and control that as well. So for example, they've got the leaf string there, so again that's fundamental. They look at the deformation, the forces on that to do that. It also has this eternal kind of pipe for the compressed air to get to the knife. But the knife itself really is where the key innovation is itself. It's actually porous to kind of do that. So again, they've modified their parameters, they've done that, and almost created a different material in that sense. So if the mechanicals properties would be different, so it's still fundamentally stainless steel, but they've modified it to end up with a different material in essence to do the job they want to do. And again, then with the integrated hinge, how you build that in, they've had to come over look at a number of different material properties to really design that product and to be able to do it in one part. As you can see on the left, this is our large kind of platform. You fit all the parts on there and build them all in one go with all these different properties of the materials to kind of do them. So now also another one of our partners and customers again. So again, they're using the materials in different ways. So this is Cyber F1 Racing, and the application they're using it for there is wind tunnel testing. So all the parts you can see are actually wings and aerofoils, parts from F1 cars. And what they found is that through our technology now and the price cost reductions we can do, actually they're able to use metal instead of what they've traditionally used is SLA, and then we're competing with them to be able to do that. And again, that's my part about materials and then process development to drive down the cost in new applications. This is a good example of that. And the benefit of using metal over SLA is that it's much more rigid. So they get much better results by testing that on their wind tunnel results. F1's very strict about the amount of wind tunnel time you can have, and because these parts are much more rigid, they can do much smaller iterations and really make some key benefits over that itself. And as I say, from a materials point of view, the density and things they're less worried about. It's speed, it's production of the parts they do that, and really here it's the surface finish is the key part, as well as the improvements in the rigidity of the part itself. So again, one kind of final then look at this is also someone else we're partnering with, so the SMS group, and they're looking at kind of the whole turnkey integrated factories part to do that. What they want to show is really integrate the whole kind of process chain itself, really from powder production all the way then out through the part, including heat treatment, quality checks, and everything else to do that. And for me, what's interesting particularly there is from a materials point of view, I won't go through all of these, but what's really interesting concept is that all the material gets recycled as well. So any support structures or any kind of outputs that is out of size from the atomization process then gets all recycled to do that. And that really helps from that quality point of view. So I was talking about the data earlier, knowing really, the traceability, the quality of your parts coming in, not exposing your powder to oxygen as well, has a number of real kind of material benefits that really help with the process and the statistical parts you need to go really into the process of industrializing this technology to do that. And I think the final point that I want to make as well, just because I'm a material scientist from that point of view, I think people often look at a data sheet and think that's the only kind of properties you get. Additive industries, we want to think about the whole kind of process chain itself, and that includes the heat treatment as well. And I think all this graph is really trying to show you can modify those properties to what you want as well to do that. Obviously standards and everything else is great for aerospace when you want suppliers to be able to supply to all the same process. But when you're F1 or K3D or whatever else, it's very much your application to do that. So as long as you can control all these processes and do them in a repeatable way, you can really start to add benefit downstream as well, and that could be post-processing, surface finishing, heat treatments as well. There's a lot more you can do, and I think that's the point I'm trying to make. The process itself, so AM technology is great. We have all these parameters and things you can change. I think really maximizing all those gives the engineers a lot of leverage to design, do different materials, different features, change your microstructure as you go through to do that. But we must think of it as a whole process, and the materials are a key part of that. So I think my time's coming to an end, but just then in conclusions, I think definitely more material choices on its way. As I said, particularly from aerospace, we're really starting to see some improvements there. But I started the presentation off by saying several of factors affect that, and material composition is definitely one of them. So some materials are not best suited for the process to do that, but historically people wanted to use them because they've had other data on it. The process and the parameter sets clearly have an effect and on the parts you produce, and the business case as well is an important part of any process to kind of do that. And then in the future, I think traditional alloy development has always been by trial and error, and has taken forever, over decades. But I think information really, again, is the key then. Use it with artificial intelligence. We can develop a lot of new materials and really end up with the applications we want, with customers using the materials they really want to be doing it in. And then, but also, as I mentioned in the last slide, so, the raw materials, the input to the process, there's lots of levers and dials we can turn as engineers to really make the parts we want, with the properties we want at the end of it all. And something I'm very passionate about is, we see these general material parameter sets. I think we should get to much more feature-based parameters to do that, to enable that finer detail, really apply those applications further to do that. So thank you. That's the end of my presentation. I believe we do questions at the end, but thank you very much.